Good day, class. In this lesson, we will learn to work with the sum and difference of perfect cubes. Remember that this is a quick method that we will use to factor special products, binomials in particular, remembering that binomials have two terms. Let's take a look at special products very quickly. Recall the difference of perfect squares. You should have already completed a lesson based on the difference of perfect squares. Here's an example of a binomial that represents a difference of perfect squares. The x squared is perfect. It's a perfect square, x times x. 64 is also a perfect square, 8 times 8. And we have opposite signs here. One happens to be a positive term, the x squared term, and the other happens to be a negative term, the 64 term. This is an example of a difference of perfect squares. Also, I'll skip ahead a bit and we'll take a look at the perfect square trinomial in another lesson. This is also a special product in which you can quickly factor it based on a standard or a formula. Be sure to review your perfect square trinomials lesson that is very similar to this one. In this particular lesson, we're going to talk about the sum and difference of perfect cubes. So here is an example of a perfect cube. Notice how on the left we have x to the third power, or x cubed. This is x times x times x, so clearly this is a perfect cube. Also, we have 27, which if you'll recall is 3 times 3 times 3, which happens to be a perfect cube as well. And if you notice here, we have a difference of the two terms. So let's take a close look at perfect cubes. First, recognize that a perfect cube would be a number raised to the third power. If I expand, for example, 1 raised to the third power, it's really 1 times 1 times 1. And then, of course, 1 times 1 times 1 is 1. Let's take a look at 2 raised to the third power. Expand that, it's really 2 times 2 times 2, which essentially the 2 times 2 makes 4, and then that value of 4 times 2 makes 8. And then we could just carry this out to its logical conclusion, where we have 3 raised to the third power, which is 3 times 3 times 3, which yields 27, and so forth and so on. And then you begin to recognize these perfect cubes because you use them rather often. So the more you use them, the more you recognize them. So we'll be sure to practice as much as possible so that we can quickly recall some of our perfect cubes and move very quickly through some of our rearranging of equations, which is the purpose of this lesson, so that we can prepare as we move forward to be able to alter our equations to quickly get them solved. Moving right along, let's go into an example. Here we have a difference of perfect cubes. And so we're looking at x raised to the third power minus 27. Now, anytime I'm trying to manipulate an equation in the future, I may need to factor particularly a special product. And I want to get it factored, so maybe something might cancel for me. And that's what I'm looking forward to. So right now it's important that I learn how to deal with something such as this, x raised to the third power minus 27, because it can be rewritten in a different form. So I'm going to factor it. I'm going to learn to factor it, recalling that there is a formula that we use, and here is the formula. The formula says that we can rewrite it this way. We can take our a minus b in a quantity, and we can also, in a separate quantity being multiplied by our first quantity, take our a squared plus a times b plus b squared. And this is the same thing that we started with. Now, you may be wondering about that a and that b. My first term will represent my a, and my second term will represent my b, if you will. And keep in mind that b is really, in this case, 3 times 3 times 3. So b is really 3. So keep that notion in the forefront of your mind that 27 is really 3 times 3 times 3, since the cube root of 27 is 3. So let's carefully piece this together. Following the formula that I've been given, I'm going to go with a first. So that's just going to be one of those x to the third term. So we've got x times x times x. The a is represented by x. So I'm just going to go ahead and pull one of those x's and put it there. I'm going to go ahead and pull one of those 3's. Remember, 27 is represented as a cube root or as a perfect cube, it's 3 times 3 times 3. So I'm just going to pull one of them because my format here, my formula is telling me I just need B, just one of those. And then for the my second factor, I'm going to go with my squared value. So I want a squared. So I want two of those x's, if you will, or x raised to the second power, x squared. And then I'm going to use my a. I'm going to use my b. We're calling that x is representing my a and 3 is representing my b. And then I'm going to use my b squared. Or, of course, in other words, 3 is getting squared. So now I'll recognize that really, if I simplify what I've written here, I really have in my first factor, x minus 3. And in my second factor, this quantity is x squared plus 3 times x plus 9. These have the same value. Our original, which is x cubed minus 27, and our factored form, which is the quantity of x squared minus 3 times the quantity of x plus 3, x plus 9. Remember, the purpose of this is as we move forward, we may need the factored form so that we can manipulate equations. So as of now, we're practicing getting into the factored form. Let's move right along. Now we're dealing with the sum of a perfect cube, sum of cubes. So we have a perfect cube. We've recognized that. We've got x cubed plus 27. So I stuck to the same example so we can be a little bit consistent and kind of remember and practice where we're going. But it's now a sum of perfect cubes. Notice how the equation or the formula, if you will, changes slightly. Pause it. Make sure you've written down the formulas. They are different for the sum of cubes and the difference of cubes. Remember, someone has written these formulas for us, so we simply want to employ them. I have my formula. I'm going to fill in my blanks. We're calling that my A's are represented by my X's in this case, and my B's are represented by my 3's, if you will. We're calling that 3 times 3 times 3 is 27. So I'm going to utilize my formula, substitute my values the same way we did in the previous example, and then you simplify after you have substituted, and now you have the factored form of x cubed plus 27, which will serve us quite well in the near future. One last thing I like to demonstrate is the double checking of your factored form. So let's go with our sum of perfect cubes. If I start with the sum of perfect cubes and I have x raised to the third power plus 27, and I factor that and say that the factored form of this is x plus 3 quantity times the quantity of x squared minus 3x plus 9, then I need to verify that that's actually true. So remember, factoring simply means to unmultiply. So drawn out to its logical conclusion, if you multiply those factors back again, you should get what you started with. So let's practice that. I'm going to multiply back out these terms or these factors. Let's start with the x times the x squared. That gives me my x cubed. And then my x times negative 3x. That gives me my negative 3x squared. My x times my positive 9x. The 3 times x squared is 3x squared. The 3 times negative 3x is negative 9. And the 3 times 9 is 27. Now, of course, I'm going to simplify my like terms, but I'll notice, first of all, that I've got some cancellations here. I'll go ahead and cancel those and simplify. And so I can actually verify that my original expression, x raised to the third power plus 27, is the same actually as my factored form.